Ah, welcome back. I hope you were all able to enjoy your break as best you could, however you could. Um, I know we're just jumping right back into things, and I know that we're going to have the rest of the year like this, and it's going to be a little bit different, but I promise you, I will not waste your time. I want you to learn some basic physics so that when you go to college next year, or when you come into my AP Physics class next year, you will have a basic idea of some of these things and will be versed enough uh, in the basics so that you can kind of prove your understanding of physics. Before break, we were talking about free body diagrams and friction and all that great stuff. I just want to let you know, those problems could get way more complicated with angles and sine and cosine, but because we just don't have time, I decided I don't want to focus on all that trig stuff, the sine, the cosine stuff, so I'm probably not going to, we're not going to see sine or cosine much. I'm not going to say at all, much for the rest of the year. I do want you to know I am going to cut some of that out. But in essence, we have done the first two of Newton's laws. Newton's first law says objects at rest tend to stay at rest and objects in motion tend to stay in motion in a straight line unless acted upon by an outside force. Newton's second law says the net force equals the mass times acceleration, where force and acceleration are directly proportional, mass and acceleration are inversely proportional, and the object accelerates in the direction of net force. We haven't had time to kind of go back and talk about Newton's second law and what all that means. But if you really think about it, if you look in your notes, if you listen to me say that definition again, you will understand that we actually do kind of know that. We know that free body diagrams accelerate in the direction of net force. The arrow that's biggest is the direction it's going. We know that if you have more mass, you will have less acceleration. We understand that. We know that if you push something harder, it will go faster. The force acceleration are directly proportional, and we are pretty good with the FEMA equation at this point. So even though it seems like I don't understand how all this is connecting, I don't want you to lose sight that everything that we've been doing connects directly to one of Newton's laws. So it is high time that we get into the last law, Newton's third law. The picture below is of a Newton's cradle. And fortunately, we all had an opportunity to play with these before our quarantine break. It is a great example of Newton's third law. Newton's third law. Reaction, there's always an equal and opposite reaction. It's the least verbose of his three laws. That's it. There's no equation, it's just that. For every action, there's always an equal and opposite reaction. However, this is the most misunderstood law. What he's saying is, if you touch something, it touches you back. Always. So, you may not believe me. So if you look, if you're at the joy of sitting at a computer desk or a wall or you're on your bed, here you can do a quick little demo of this. You can take your hand out, stick your finger out, and your finger is totally straight. And as you press your finger against your bed, your wall, your desk, you could see the tip of your finger bend. Why is your finger bending? Are you making your finger bend like that? No. The reason it's bending is because as you push the wall, the bed, whatever, it's pushing it back. And the wall pushing against your finger is causing it to bend just a little bit. Action, reaction. Another common example is if you are boxing and you kind of shadow boxing, if you hit the wall softly, it doesn't really hurt your hand. However, if you hit the wall very hard, you could potentially break your fingers. Action, reaction. If you hit something harder, it hits you back harder. So when I look at this picture right here of a swimmer, she's in the water. If she pushes against the wall pushes her away. Her feet push the wall pushes her feet. It is an equal and opposite reaction, and that's why she moves, because of those pushes. Forces always must exist in pairs. If you are hammering a nail, when the hammer hits the nail, the nail goes in. But if you don't, that's obvious. Obviously the hammer hits the nail. But did you know the nail also hits the hammer? How do you know that? Think about it. The hammer was moving. Then the hammer stops moving. How does something can't stop moving unless there's a force? That's what Newton's second law said. So if you were hitting the hammer, the reason it stops moving is because a force stopped it. Where did that force come from? The force came from the hammer. If you have ever been in a boat or a raft and you try to walk, you may notice that if you're in a small enough boat, that if you walk forward, you might actually push the boat back. This is, if you think about it, walking happens through action-reaction pairs. What do I mean by that? When you walk, if you're walking, there we go. Bam, there you are, looking good. Glad you guys are taking care of yourselves in this break. Looking good. What happens is your feet pushes your feet. Feet push floor. Okay? And then what happens is the floor pushes your feet back in the opposite direction. And that's why you go. Floor pushes feet. This is why you move. If you try to walk on ice, ice can't push very hard. That's why instead of moving forward, what happens is your foot slides. It doesn't have enough friction to go ahead and actually push you forward. If you're on an old rickety deck that's kind of falling apart, if you push against it too hard, instead of it pushing you forward, you might cause it to break. So if things can't push back with the force that you give it, they either move or they break. But if you walk on the floor and that floor is still there, so you push the floor, you push it back. You push the floor, it pushes you back. Newton's third law of motion in action. So let's talk about some of these action-reaction pairs. The reason why your car can drive and the reason why it physically moves is because the tire pushes the road pushes the tire. This is action-reaction. So generally, this is what you want to think about it. If A pushes B, and A and B are objects, then B pushes A. So another example that I like to do, unfortunately we can't do this in class, but I'm going to describe it for you, is stand up straight. Stand up straight in the middle of your room. Keep your feet touching together. Your heels and your toes are as close together as you can. Try to push something without falling back. If you have a sibling, call them over and push them. You cannot push them without getting pushed back. And you will feel it because as you push them, you will actually fall back. What happens is when you push, you get pushed back. That is Newton's third law. You will lose your balance. And what you'll have to do is you might have to, depending on how hard you push, you might have to step back to catch yourself, to cancel that force. But if you don't believe me, you could put your feet together, you could go to a wall, push the wall, and then tell me that you don't get pushed back. Action, reaction. A lot of people want to know how rocket ships move. Rocket ships, what they do is they have a bunch of gasoline. As they burn, they push the gas out, and then that's the action, and then the reaction is the gas pushes the rocket forward. That's why rockets could fly in outer space, because they're not pushing off anything, any matter. They bring the matter with them and they push it out. That's how a rocket works. A man pulls on a spring pulls on man. So essentially, the verb that we're going to use to connect these words is pushes or pulls. Now, the thing that I want to bring up that's a little bit confusing, it doesn't make a lot of sense, is if you drop a ball from a building, we all agree that the earth pulls on the ball. We call that gravity. That is the earth pulling on the ball. But earth can't pull on the ball unless the ball pulls back on the earth. Action, reaction. The ball is technically pulling on the earth. However, when you drop a ball, it's not like the ground flies up into the air to meet the ball. No, the ball falls. What is the difference between a ball and the earth? The mass. And we know that mass and acceleration are inversely proportional. So because the earth has a huge mass, it's going to have a teeny tiny acceleration. Because we know the ball has a small mass, it's going to have a fairly big acceleration. The forces are equal. Force equals mass times acceleration. So the Earth isn't really moving because the ball pulls on it. It's not strong enough to actually get it to move. It's so microscopic it can't even be measured. But technically, if the Earth is pulling on something, it's pulling it right back. So everyone always asks me, okay, Bizzuto, what happens if we just got everyone to drop something at the same time on the planet? Could we move the planet? Well, think about it. The planet is circular. Well, spherical, really. And people live all over the world. And gravity is pulling them all to the center of the Earth. So if people, if people drop things and it's pulling the Earth this way, and then people here are dropping things, it's pulling the Earth this way, well, those forces cancel out. Because don't forget, the Earth is round. And another question that people ask me is, if everyone gets in the same spot, if all 7 billion people are able to stand in the same spot, they can't, and jump at the same time, would that be enough force to move the Earth? Honestly, no, it really isn't. The mass of the Earth is so huge. It just is such a negligible force. You will not be able to do that. So I want to get into space because space is really important. All movement occurs because you push off of things. If you have nothing to push off of, you can't move. If you have nothing to push off of, you can't move. So when you're in outer space, there's nothing to push off of. If you're floating in outer space, no matter how much you move your arms, your legs, unless you push or pull something, you will not move. And here's a fairly old photo, but it really illustrates the point. When astronauts would go in for spacewalks, they would always have a safety cord. That cord is not giving them oxygen. They have oxygen on their backs. What they have is a tether, so that if something goes wrong, they could physically pull themselves back to the space shuttle. That is the point. And if you ever see science fiction movies, space movies, and again, you should go watch Gravity. You have a bunch of time, maybe. I don't know. You may not have time. But if you do, go watch a science fiction movie called Gravity. It has pretty good, not perfect, but pretty good physics. And you'll see that, like, when they go out into space, they have these little tethers on. Or they have a little rocket ship thing on that they could go ahead and, again, as I said, rockets push gas back, and that gas pushes them forward. That is the essence behind all motion. If you can't push off of anything, you don't move. If you have a swivel chair at home, try to get into that swivel chair and try to move in that swivel chair, to roll across the room without touching anything. You'll have a lot of trouble. Okay, let's get to the nitty-gritty, the math. This isn't so bad. It's actually going to be quite easy compared to some of the other math we've been doing. So this is what I want to show you. Little Susie is floating next to Nellie Newton in outer space. Okay, so here's little Susie. There she is in all her glory. Here's Nellie Newton. Okay, great. Love it. I am going to make this basic little chart. They're each separate. They're going to have different masses. They're going to have different accelerations. So this little dotted line in the middle is the separation between them, just so you know that I know they're separate. Little Susie has a mass of 40, so under Susie, I'm going to put 40 kg, Mars rover, of course. And Nellie Newton has a mass of 50, so 50 is going right there. Okay, here we go. Nice. If little Susie pushes Nellie Newton to the right with a force of 200 newtons, so she pushes him right 200 newtons. What is the acceleration that each of them experiences? Okay, well, it's going to be really easy to get his acceleration. I have his force, I have his mass, and I can just FEMA that. I could just plug those numbers into that equation. 200 equals 50. A divide. He is accelerating 4 to the right. Okay, that was easy. But how do I get her acceleration? Well, they're in space, so we don't have to worry about gravity. All these problems that could be in space. We don't want to worry about gravity yet. We're just going to be floating out there. So if she pushes him to the right, Newton's third law says he actually is pushing her to the left with a force of 200 newtons. Equal and opposite. Their forces are the same. She cannot push him 200 newtons without getting pushed back 200 newtons. So now I'm just going to use FEMA again for her, plug in the 40 and the 200, and she's going to have an acceleration of 5 left. So that's going to be a negative 5 meters per second squared. Oh, and you know what else I noticed? The person with more mass has less acceleration. More mass, less acceleration. The person with less mass has more acceleration. That's inversely proportional. We did that before break. Nice. Okay. Pushing with the third law continued. Now we have a 600 kilogram cannon. Ooh, okay. There we go. Cannon. Yes. Like old school Revolutionary War cannons. Okay. There it is. That was, well, art was hard. I'm going to make the same generic picture that I made last time. Mass equals, acceleration equals, and then there's going to be a force this way, be a force this way. Okay. So if you ever see a movie like, I don't know, Pirates of the Caribbean or something, and you see them firing the cannons of the ship, you might notice the cannons roll back. That's called recoil. That's very real. A recoil of firing a cannon back is real because if that cannon is pushing the cannonball forward, then that cannonball is pushing the cannon back. That's actually very correct in terms of physics. So let's go ahead and throw some numbers in. So we have 600 kilogram cannon, mass 600. Okay. And the cannonball's 30. Okay, there we go. And the cannonball accelerates positive 40. Okay, great job. Nice. What is the acceleration of the cannon? Wait a minute, I don't get the force. Oh, take a look at this. On the right side, I have the mass and the acceleration. If I multiply the mass and the acceleration, FEMA, I can get the force. 30 times 40 is 1,200. Yes. If the cannonball is pushed to the right 1,200 newtons, that means the cannon is pushed left 1,200 newtons. Oh. You can just FEMA again. This is easy. 1,200 divided by 600 is negative 2. Wait a minute, Bazooka. I thought 1,200 divided by 600 is positive 2. Direction. Look at the direction. That's it. This one is fairly simple. It's the exact. Sorry, I should have been. Sorry, I was getting into the question. I was reading it and solving it myself. Got the two people again. All right. Little Susie. So again, this is the basic picture that you draw. You draw two people, two objects. Doesn't matter. Got this. And they're going to have equal and opposite forces. So this time we know this is little Susie because of the hair. Little. I'll put LS. So we know. LS and NN. Okay, she's got a mass of 40. Now, little Susie accelerates -6. So one thing people will mess up in is they won't read carefully and they'll put like the wrong acceleration next to the wrong acceleration next to the wrong person. So just be mindful of that. Nellie Newton is the one who accelerates +3. All right, cool. Okay. Oh, this is the same thing as last time. Instead of solving for the acceleration, we're solving for the mass. In order to do that, though, we need to get the force. We don't know Nellie's force, but we know Susie's force. 40 times -6 is -240. I'm just going to put in as 240 because when it's next to a left arrow, that means the same thing. If that's 240, that means this is going to be 240. So the mass, 80. Nice. Oh, by the way, acceleration is halved, the mass is doubled. That's like some sort of inversely proportional relationship. Okay, your homework. Your homework is going to be a few things. We did some concepts. I haven't done a lot of concepts before with you. I've really kind of been focused on the math, but I do need you to kind of understand these concepts. So your homework is going to be twofold. It's going to be a Khan Academy and a worksheet. It's just 4 questions of Khan Academy. And if you did not get what you needed to get out of this, feel free to listen to Sal Khan explain Newton's third law to you. Hopefully that would make more sense than what I've done if you are really lost or if you don't want to reach out to me or whatever. We are going to have a worksheet and we're going to have a Khan Academy. I want to do a few questions on the worksheet together in this PowerPoint just so you have an idea as to how to do this. So action-reaction pairs. So little Susie walks down the hallway and bumps into Nellie Newton. How do I do this? Action-reaction. Okay, well if little Susie walks down the hallway and bumps into Nellie Newton, the action is little Susie pushes Nellie Newton. Action. If A pushes B, then B pushes A. Then the reaction is that Nellie Newton pushes little Susie because she can't push him without getting pushed back herself. Okay, little Susie walks along the floor. Action. Little Susie pushes floor. Okay. Bizzuto, I don't get these questions. Essentially, all you need to do is identify the 2 objects that are interacting and put the word push between them. It's little Susie walks on the floor. You can't say, I mean, you could say little Susie walks on the floor, but you can't really say the floor walks on little Susie. So walking really is pushing. So we're going to use the word push. Floor pushes little Susie. Great. Nellie Newton talks a lot. When you talk, what are you pushing? Air. Nellie Newton pushes air. Air pushes Nellie Newton. Little Susie swims. When you swim, the reason you're able to move is because you push water. Little Susie pushes water. Water pushes little Susie. I want to keep this moving. A ball falls to the ground. We talked about this. The earth pulls the ball. Understand the relationship that exists here. Oh, okay. A minivan. This is important. This is a concept question. A minivan is driving down the road and hits someone on a bike. Which of them experiences more force? Now, I know your gut instinct is to say, oh, of course, the biker is feeling more force. Technically, that's not true. The minivan hits the bike hits the minivan. Same force. The forces are the same. However, what's different is the consequence of those forces. That force doesn't do too much to the minivan, but that same force could really injure a biker. So they experience the same force, but the injury comes in terms of the acceleration. Who is going to accelerate more? The person with less mass. So who has more acceleration? The biker. And that's why the biker will get thrown around, because they have more acceleration. Okay. I know we only have this one lecture this week, and I know I put a lot into it, but hopefully it's not too bad, and hopefully this gives you a good concept of Newton's third law. If you are utterly lost and have no idea what you need to do, I'm here. I'm now going to have daily office hours where I can help you out, or if you want to just come in and chat, that's fine. Those will be from 12:30 to 1:30 every day, and yeah, we're gonna make this work, guys. We are. Be well, and I will see you guys next time.